Good morning, everyone. I'll just wait for a little bit. My apologies. So, when I woke up this morning and I saw Microsoft Teams wanted to update something, that's when I got a severe sense of dread that something might go wrong technically. I think MS Teams might have, by its own accord, separated this meeting into two different links. So some people might be joining a separate meeting with this exact same link. So I posted over there. So hopefully more people will come over here. Right, maybe we'll get a start, and whenever other people join in, I'll be recording this meeting. So if you do not wish to be recorded, you can always look into the recording afterwards. Okay. Thank you very much for joining today's online seminar. So my name is Yuja, and I'm very delighted to present our speaker today, Professor Zhan. Professor Zhan is a professor at the School of Mechanical Engineering and Automation in Beihang University in China. He received his bachelor's and master's degree from Beihang University in China, and then did his PhD in Kyushu University in Japan. He then did his postdoctoral research positions at the Japan's National Institute for Materials Science before serving as a researcher at Waseda University. And he was then an associate professor at Toyo University in Japan before moving back to Beihang University as his professional position at the moment. His research interests are in nanoscale thermal transport, micro-nano fabrication techniques, thermoelectric energy conversion, thermal interface materials, and thermal management of semiconductor devices. So we're very grateful to have such an expert on thermoelectric energy harvesting today. And I'll hand over to Professor Zhan if you would like to share your slides for cavity-free silicon nanowires thermoelectric generators. The share button is on the top right. Yeah.
Okay, can you see my PPT?
Yes, perfect. Thank you.
Okay, so let's get started. So first of all, thanks to the organizer, Professor Jia, for giving this opportunity to give a talk on my research, and I'm very glad to have this opportunity to communicate with all of professors and researchers. And so the title of my talk is cavity-free silicon nanowire thermoelectric generator for energy harvesting. And my name is Tianzhuo Zhan, and from Beihang University in China. Okay, so first, I will give a brief introduction of thermoelectric generator. And so, in IoT society, and sensor networks are used for collecting data, various data for monitoring, as structure health monitoring and safe monitoring, and etc. And so, but the power supply of the sensor networks meets challenges because all cables and batteries need to be eliminated in remote and harsh locations, and also some inaccessible areas. And so energy harvesting is a promising candidate to solve this problem. So we know that there are various energy forms we can harvest from.
Excuse me, sorry. I think the slides is not turning.
Huh? Okay.
Maybe when it's in full screen, maybe it doesn't turn.
Oh, so how about now?
If you can.
So
are you in the next slide?
So you cannot see the slide now?
It's still showing the first slide.
The first slide? Okay. Okay.
A couple of days ago, it's easier to share the screen and then
Send screen. Okay, I will change to share screen. Okay. Okay.
Yeah.
Okay. So how about now?
Yes, perfect.
Okay now. Okay.
Yeah, it's good now. Yeah.
Okay. So let's continue. There are various energy forms we can harvest from the environment, and but the energy, the power density we can harvest in this form is typically very small, typically from the microwatt to milliwatt per centimeter, square centimeter. But so with the advance of sensor technology, we know that the power consumption of sensors has been decreased to a very low, extremely low level. For example, in a standby mode, it's only in a nanowatt level, and even in active mode, it is microwatt to milliwatt. So practically, we can use the energy harvested from the environment for the power supply of ultra low power IoT devices. And so our thermoelectric is one of promising candidates to solve this problem. So when we apply the temperature difference on some electric materials, so a current will be generated, and because of the seeback effect, and the thermoelectric materials has been used for deep space exploration, and in the form of a radioisotope thermoelectric generator. And the thermoelectric materials has various has many advantages, and for example, it's a direct energy conversion and needs no maintenance, and also noiseless operations. But some electric materials also have limitations. The biggest one is that the efficiency of TEGs is very low. So the efficiency of TEG can be calculated using the dimensionless parameter ZT of the thermoelectric materials, and so we know the present thermoelectric materials ZT is around 1, and so we can calculate the power efficiency of the TEG is lower than 10%. So the aim of the ZT value is around 3 or 4. So if we can increase the ZT value to 3 or 4, so we can improve the efficiency of TEGs to more than 20%. So for the some electric materials, so the typical materials used for practical use is bismuth telluride and antimoney telluride, and also lead tellurides and their alloys. And so the ZT value is around 1. And but we know there are some limitations for these materials. For example, the element tellurium is rare, and also all these materials are not CMOS compatible and also non-environmental friendly. So we need to find materials to solve these problems. We found that the silicon is a promising candidate because silicon is abundant and CMOS compatible and also environment friendly. But the problem is silicon has a very low ZT value, is around only 1.01, 0.01. So, but in 2008, 2 articles published on Nature and so that if we fabricate silicon to the form of silicon nanowires, so we can enhance the ZT value from 0.01 to by 1 to 2 orders of magnitude. For example, in 200K, we can get a ZT value around 1, and even in the room temperature is around 0.6. So this is because the thermal conductivity of thermoelectric materials is significantly decreased by phonon scattering due to the small feature size of the silicon nanowires. And so since line various silicon nanowires, TEGs have been developed, and including the planar type and also the vertical type. And so for both type silicon nanowire TEGs, we need to etch the materials surrounding the silicon nanowire to cut off the heat flow way, because to form efficient temperature difference. But this process results in some problem. For example, has a very high fabrication cost, and also has a fragile structure. So we proposed a new structure that's a captive-free silicon nanowire. And this is the schematic diagram of this structure. So we use the CMOS process technology to form silicon nanowire using SOI silicon on insulator substrate. And so we do some simulations to see how much temperature gradient we can form. And so in this TEG structure, so if we applied a temperature difference in the vertical direction, so the main heat current flow from top-down vertical direction, and so this is the main current. But some currents also flow in the planar direction, is the XY direction. So we can see a very steep temperature gradient can be formed in near the heat source, and also most of the temperature difference formed in the very near place of around the heat source. So if we can use this steep temperature gradient, we can generate a large power density using this kind of TEG structure. And we have do some performance simulation, and this is structure, and we change the length of the silicon nanowires from 1 micrometer to 50 nanometer, and we found like so the power density has been improved by 100 times by shortening the length of silicon nanowires. And we still have some problems if we want to further improve the performance of TEGs because the parasitic thermal resistance in TEG is very big. So this is a 3D schematic diagram of the TEG. We can see that we have a silicon substrate and also a heat guide layer to facilitate the heat spread from the heat source to the hot side junction of all the thermoelectric modules. And so we know that only the temperature across the thermoelectric modules can generate power, and the other part of the TEG cannot generate power, and only waste temperature difference. So we need to improve. We need to decrease the parasitic thermal resistance in TEGs to improve the power density. And so first of all, we know that the thickness of the silicon substrate is very large. It's around 745 micrometer. So if we can thin the silicon substrate, we can change the temperature difference across the silicon nanowire, and then we can increase the power density. And so the simulation results show that the power density has been increased by more than 2 orders of magnitudes. So by thinning silicon substrate from 745 micrometer to 50 micrometers. And we also fabricate the silicon nanowires using the CMOS process technology, and so we use the backside grinding technology to thin the silicon substrate, and so like the experiment results also show that the power density has been improved by more than 10 times by thinning the silicon substrate. And so we also measure the thermoelectric properties using a live-built measurement system. We use a micro heater to heat the hot side junction, and also we use a chiller to cool down the cold stage, and this is act as a cold side junction, and then we can form a temperature difference across the silicon nanowire. And so next I will show you how to optimize the heat guide layer to decrease the parasitic thermal resistance. So the heat guide layer should be thermally conductive and also electrical insulative, and so this table has shown the materials with a different semiconductivity, and also the electrical conductivity. And we know like diamond has the highest semiconductivity, but it's very difficult to form a high quality diamond thin films using a low temperature, and typically we need to use the temperature more than 1000 degrees to form high quality diamond thin films. So we So we found that aluminum nitride is a good candidate because aluminum nitride has a high conductivity around 300 watt per meter per Kelvin, and also it's a good electrical insulator. And so we deposit aluminum nitride layer on the hot side junction of the TEG, and by two kinds of method. One is a non-reactive sputtering method. It means like we use argon gas and also aluminum nitride target. And another one is a reactive sputtering method, and using argon plus nitrogen sputtering gas, and also aluminum target. And we measure the part generation of the two kinds of TEGs, and we found like the reactive sputtering has a better performance than the non-reactive sputtering one. And so we use the frequency domain thermoelectric reflectance method to measure the semiconductivity of the aluminum nitride thin film, and so we found like the aluminum nitride thin film deposit using the reactive sputtering method has a higher semiconductivity than the non-reactive sputtering method. But both of these two samples has significant lower semiconductivity than the bulk aluminum nitride. And so this is because we observe the TEM image and also do characterization by the XPS depth profiling, and we found like the crystalline quality for aluminum nitride thin film is very poor. For the non-reactive sputtering method is totally amorphous for phase, and for the reactive sputtering one, only very small crystalline can be observed, and the quality is very poor. So this results in the very low semiconductivity of the aluminum nitride thin film. So that means like aluminum nitride thin film deposit by sputtering method is not a good candidate. So we need to improve the semiconductivity of the heat guide layer. And so next, we design the metal dielectric heat guide layer. So we know that metal thin film has a high semiconductivity, but they are conductor. So we need to use a dielectric layer to fall electrical insulation. And so we use two kinds of metal. One is aluminum and copper. The other is copper. And two kinds of dielectric material, silicon dioxide and also aluminum nitride. And we also use some two kinds of adhesion layer. One is titanium and the other one is chromium. And so to improve the adhesion between the metal layer and the dielectric layer, so we use a different combination of this layer to form different heat guide layers, and we measure the power generation of all these TEGs, and we found like the open circuit voltage and also the power density increased with decreasing thermal resistance of the heat guide layer. And so we also calculate the thermal boundary resistance of these heat guide layers. We found like even though aluminum has a lower semiconductivity than copper, but the sample with aluminum layer has a higher has a lower some boundary resistance, so results in better performance. And so therefore, aluminum is better than copper as the metal layer in the heat gun layer. And also we found like some boundary resistance decrease with the increase the bond dissolution energy. And so it means like the higher the bond dissolution energy, the strong the higher the bonding strength between different layer, and the results in a low some boundary resistance. And so if we compare samples using titanium and chromium, we found like titanium has a better performance than chromium. And this is because titanium has a lower some boundary resistance. And so we also do some XPS characterization of titanium and chromium sample. We found like all the titanium were oxidized, and for the chromiums, only part of the chromiums were oxidized. So this oxidation of titanium maybe may facilitate the heat transport between different layers. And also we have observed the EDS mapping of different samples. We found like the nitrogen are easy to diffuse into the titanium layer, but a little difficult to diffuse into the chromium layer. And this is also a possible reason for enhancing the heat transport between different layers, results in a lower some boundary resistance, and then a higher some electric power generation. And so finally, I will summarize the results. And we found like the power density can be improved by shortening TEG lags, and also by lowering parasitic thermal resistance. And so for the heat gun layer, so even though aluminum nitride has a high semiconductivity, but thin film form performs very poorly. And also for the metal dielectric heat gun layers, we found like aluminum is better than copper due to its lower TBR, and also titanium is better than chromium due to its better bonding performance between different layers, resulting in a lower TBR. Okay, thank you for your attention.
Thank you very much for the amazing talk. And the floor is now open for questions. Ahmed?
Okay, thank you. So good morning, everyone. Thank you very much, Professor, for the interesting presentation. My question is related to the manufacturing of the TEG, of that material. So I'm just wondering, how does the manufacturing or fabrication technique will affect the performance of that nanowire material?
Okay, so thank you for your question. And I have shown you like in this page, and we have before the manufacturing of the TEDs, and we do some simulations to testify the shortening of the silicon nanowire can result in a higher power density. And so this is because we can, if we shorten the silicon nanowire legs, and we can form a very steep temperature gradient near the heat source, and then we can. So even though this one. So even though the temperature difference is becomes smaller when we shorten the silicon nanowire, but the density, the power density increased significantly. So this is the principle we design this kind of a TEG, and so also we have confirmed that the power density also increased in the TEG fabricate using the CMOS process technology.
Great. Thank you so much. Thank you.
Thank you.
Chris, I think you would like to ask.
Yeah, I was just going to ask in terms of sort of applications and sort of scaling up. Is the aim that this is sort of relatively sort of low power level, so the device structures are small, or people say about 50% of all our energy being waste heat, and so we need to capture that, but that needs large areas. So I'm just wondering about applications and scaling, really.
Yes, very good question. So the advantage of this kind of TEG is that it can be fabricated by let's say CMOS compatible process technology. So first of all, we can integrate this kind of TEGs into some silicon-based chips. So we can do some active cooling using this kind of thermoelectric, this kind of TEG. But maybe we of course maybe we need to because due to the low efficiency, we need to maybe consume more energy for cooling the chips using the Z-back effect. But so we can, because it's CMOS compatible, so it is better than other materials. So because we can integrate silicon TEGs, nano TEG to silicon chips. And another one is we can you just said it's size scalable, so we can shortening the silicon nanowire to very short leg, and using the modern industrial silicon industrial process technology. So this is even though the power density is very small, and so it still have some advantage to replace other materials in silicon-based devices. Yeah.
Sounds good. Yeah, no, that's great. Thank you. And is it in terms of specific? Do you think it's going to be a bit like you said, the space rover type thing? Is it space applications, or do you think it's more terrestrial and waste heat here on Earth, maybe?
So for the space applications, the materials we used is silicon germanium alloy, but it is a bulk materials, not nanomaterials. So for energy harvesting, this kind of a TEG is the power density is still low, and so maybe in the future we can find some method to significantly improve the power density. And so in my opinion, I think the most promising application for this kind of TEG is for the thermal management of semiconductor devices. Maybe in the future, if we can improve the efficiency, and we can integrate this kind of TEG for active cooling for the chips. Yes.
Yeah, lovely. Thank you, and thank you for an excellent talk. Thank you.
Thank you. Are there any other questions from the audience? Maybe while people think about questions, I have one question, Professor Zhan. So you showed us the ZL chart for the theoretical efficiency percentage in the beginning. So I was wondering, in terms of this technique that you've shown here, what do you think would be the limit on that chart?
Which chart?
Slide 7. Yeah. The ZT. Yeah. ZT.
Yes. So for the ZT value of some electric materials before 2000, the limit is 1. So we have spent more than 50 years to improve the ZT, but it is very difficult to improve the ZT value better, higher than 1. But in the past 2 decades, we have used some nanotechnology. It means like we can control the photon transport and the electron transport separately, and using the nanotechnology. And then since then we can improve the ZT value from 1 to now maybe it's around 2, and in some report the highest is around 2.5, and I'm not sure the ZT value can be improved to 3 or more using the nanotechnology, but it is still very difficult to improve the ZT value using the current technology. Maybe in the future, we can improve ZT value to a very high level, and at that time maybe some electric material can be a very good choice for energy harvesting.
Okay, thank you very much. I think there's a question in the chat. Is it possible to make the nanowires in horizontal direction instead of vertical? If yes, how would that affect performance?
Yes. So for the structure, so typically the vertical type is better structure for power generation, because we can form a large temperature difference between hot side and cold side. But for the planar one has a but the drawback for the vertical type is very high cost, because we need to use some deep etching technology to form the long silicon nanowire. But for the planar type is has a low fabrication cost, and also the structure is less fragile compared with the vertical type. But so we need to do some trade-off between the structure performance, the mechanical performance, and also the electrical some electric performance. So and also the cost. So we need to balance all these properties to see which one is the most important thing we need to solve using different structures.
Thank you very much. Are there any other questions from the audience? If there isn't any, I'd like to just thank Professor Zhan again very much for the amazing talk and also for taking questions. And thank everyone for joining. And again, my sincere apologies for the technical error we had in the beginning. Let's hope the next time we have an online seminar, it doesn't coincide with Microsoft updating Teams. So thank you all very much again, and thanks Professor Zhan. And with this, I think we'll close the session. Thank you very much.
Thank you all. So
Thank you all.
Thank you.
So I think I hope
Thank
we
you.
have a chance
Thank
to
you.
for a face-to-face communication in the future. And thank you all.
Yeah, thank you very much.
Thank you.
Thank you.
Take care.
See you.